Okay guys, Honors Pre-Calculus BC, day 2 of section 4.5, and we are starting right here underneath this squiggly line right here, and just filling in some basic information that you probably have figured out already, but here it is. A polynomial of degree n cannot have more than n real zeros. So a degree 2, a quadrilateral, not quadrilateral, silly, a quadratic can only have 2 real zeros. And if you think about a parabola, it can only cross the x-axis twice. That's it. Taking that one step further, odd degree polynomials will have at least 1 real zero. And odd degree polynomials have one end going down and the other end going up. So at some point, this must connect. These must connect in here, so there must be 1 real zero, at least one place where we cross the x-axis. It could be more than one, depending on the degree of that polynomial, but at least one. All right, now, we are interested in finding some information about the possible zeros here. So we have this idea from René Descartes, and he came up with this rule of signs. And here's what it says. For a polynomial written in standard form, so decreasing order of the exponents like these guys here, the number of positive real zeros of function f either equals the number of variations in sign of the non-zero coefficients of f of x, or else equals the number less an even integer. Oh my goodness, that sounds terribly confusing until we start going through this again. Polynomial written in standard form, so decreasing order of the exponents, the number of positive real zeros of that function either equals the number of variations in sign. So let's do that much first. So we're looking for sign changes. So from 5x to the 4th to the 2x cubed, no sign change. Both are positive. From a 2x squared, did I say 2x cubed? 2x squared. From 2x squared to a negative 6x, there's a sign change right there. There's 1 right there. And then from the negative 6x to a 5, that's another sign change. So right here we have a sign change, and right here we have a sign change. So again, the number of positive real zeros of that function either equals the number of variations in sign of the non-zero coefficients. Okay, variations in sign, we had 2 sign changes. Okay, so it equals that number of sign changes, or else it equals the number less an even integer. So the positive real zeros, there are either the number of sign changes, 2, or subtract an even integer from that, 0. There's either 2 or 0 positive real zeros. All right, let's look at this one. And the order of the exponents is decreasing, so we look for sign changes. From x to the 4th to this 5x cubed, no sign change. From this 5x cubed to the negative 2, that's a sign change. There's 1 sign change, which means then the positive real zeros there's 1 of them, or less an even integer. Well, if I subtract the first even integer from that, subtract 2, that gives us a negative. And you cannot have a negative number of zeros. So there is only 1 positive real zero in that particular function. Just 1 of them. If we want to look farther and find out the number of negative real zeros, so how many of those zeros are negative, then we follow the same idea, but we're going to look for zeros. Oops, I don't want that either. I'm sorry. sign changes in f of opposite x. We're looking for sign changes in f of opposite x. There's my whiteout. All right, so let's come down here and let's find the number of negative real zeros in each of these functions that we looked at up here. So the first thing that we'll need to do is we'll need to find f of the opposite of x. That's going to be 5x to the fourth, that won't change. Plus, if I put an opposite x in here, that won't change. That's a 2x squared. Oh, but this minus 6 times an opposite x, that's going to turn to plus 6x plus a 5. So now we look for sign changes. From this 5x to the fourth to a 2x squared, nope, both are positive. From 2x squared to a 6x, both positive. From 6x to a 5, both positive. There are no sign changes. So this graph will not hit the x-axis to the left of the y-axis. There are no negative real zeros. Okay, so right now between these two pieces of information, we can think about a graph here. It's a degree 4, positive leading coefficient, both ends up. It says there are either 2 positive real zeros, and no negatives, so it's not going to hit the x-axis down here. It might be something like that, where we have those 2 real zeros, or something like that, where we have no positive real zeros. But notice in either case, I did not hit the x-axis to the left of the y-axis because there are no negative real zeros. That's an idea of what that graph looks like. All right, let's come over here and let's look at this one. And first, let's find f of the opposite of x. So f of opposite x has to be, this will stay the same, x to the fourth. This one is going to change to a negative 5x cubed when you replace that x with a negative x, and then minus a 2. Sign changes. There's one right there from a positive to a negative. And here, negative to negative, no, there is one sign change. So that means that we have one negative real zero. And if we think about sketching this one, we know it's a degree 4, opening up. We have one positive real zero, one negative real zero. Have to cross the x-axis to the left of the y-axis once. And we'll have to cross, we need a positive real zero. Now, maybe it dips here, maybe it's just real flat in here. Not really sure what's going on, but we do know that we only have 2 real zeros, one positive, one negative. Let's look at this page. Now, what happens if we want to actually find the zeros, find what those zeros are, not just count them, but know exactly what those are? There are lots of ways we can do this. To actually find the zeros, we could draw a graph off of your calculator. Okay, type that up in your calculator and get the graph, and then use second calc 0 if they look ugly. We can factor. That'll find zeros. We can use the quadratic formula if we happen to have a quadratic equation. Or we could use something like this called the rational zeros theorem. sometimes referred to as P over Q factoring. All right, and this rational zeros theorem says if P represents all of the factors of the constant term and Q represents all of the factors of the leading coefficient, then all combinations of P over Q represent the possible rational zeros of the polynomial. All right, so if I have this equation, 3x cubed plus 8x squared minus 9x plus 2, all right, if you didn't catch that, that's okay. We're going to explain it down here when we do this problem. I want to know where this polynomial is equal to 0. So we want to find the zeros. Okay. This is not going to factor by grouping. We have 4 terms, and it will not factor by grouping. There's only an x squared common here, which would leave us with a 3x plus 8. Clearly, you're not going to get a 3x plus 8 out of this one. So let's move on. What we're going to have to do then is to do this P over Q factoring. So let's find P. P is all of the factors of the constant term. So factors, things that multiply to be 2, they are plus or minus 1, positive or negative 2. Q is all of the factors of the leading coefficient. So 3, things that could multiply to be 3, plus or minus 1, plus or minus 3. And then P over Q. That's all the possible combinations of P, each of these values over these values. So right here we're going to have 1 over 1, so plus or minus 1. 1 over 3, plus or minus 1/3. Then we did the 1, so let's do the 2. 2 over 1, that's plus or minus 2. And the last one, 2 over 3. Those are the possible rational zeros. Possible nice zeros, if you will. Now we have to just try, and we have to see what we can come up with. There are 8 choices here. Clearly we have a degree 3. All 8 of them can't work. So we have to try and figure out what's what. One of the ways that we figured this out just yesterday is by substituting in. So we could sub in 1. It's the remainder theorem, plugging in one of the zeros and seeing if you get a 0 remainder. So let's find f of 1. We'll plug that in. That's 3 times 1 cubed plus 8 times a 1 squared minus 9 times 1 plus a 2. It's 3 plus 8 minus 9 plus a 2. That's 11 minus 9 is 2 plus 2 is 4. Okay, that means we got a remainder here. That's the remainder. So that means that 1 is not a 0. All right, let's check negative 1. F of negative 1, that's 3 times negative 1 cubed plus 8 times a negative 1 squared minus 9 times negative 1 plus a 2 is 0. This is going to be a negative 3 plus an 8 plus a 9 plus a 2. Oops, we don't know that that's equal to 0. We're wanting it to be equal to 0 for that to be, for negative 1 to be a 0. We're trying to see what this is. That's 5 plus 9 is 14 plus 2, 16. So again, we have a remainder. So negative 1 is not a 0. All right, we did those two. Those are out. All right, now, one way is to use that remainder theorem and plug in these values into the function and see if we can get a remainder of 0. Another option is to do the synthetic division. To do that synthetic division. So let's try, oh, I don't want to do fractions yet. Let's take care of these whole numbers. So let's try this positive 2, and maybe, hopefully not a negative 2, but let's try that negative 2 or positive 2 first. So we're going to do a synthetic division with the 2. And again, we're looking for a remainder of 0. So let's try it 2 into the coefficients. 3, 8, -9, and a 2. Bring down the 3. Multiply. 3 times 2 is 6. Add 14. 14 times 2 is 28. -9 plus a 28 is 19. 19 times 2 is 38. 40. There's your remainder. So, -2, oh, excuse me, why do I keep saying -2? I'm so sorry. 2 is not a 0. Okay, now remember, you can do synthetic division or you can do the subbing in. And if you had subbed it in, you would have subbed in a 2 and you would have found out that that was equal to 40. So again, when you're checking these, you can do substitution, evaluation, or synthetic division. Either one works. All right, well, we've tried -2. Darn it, again, we've tried 2. Let's try -2. 3, 8, -9, 2. 3 times -2 is -6. Add, that's 2. -4, that's -13 times a -2, 26. 28. Okay, remainder 28. Ugh. All right, so that tells us that +2 and -2 didn't work. I bet you were thinking, because I kept saying -2, that -2 was going to work. Sorry, it didn't. Well, that means we need to try the fractions. Oh boy. All right, let's try the +1/3. Plugging that in, that goes into, let's see, 3, 8, -9, 2. Bring down the 3. 1/3 times 3 is 1. 8 plus 1 is 9. 1/3 of 9 is 3. Add these guys, that's -6. 1/3 times -6, -2. Are you smiling? Remainder 0. Yay! Remainder 0. This means that f of 1/3 equals 0. We have a remainder of 0, which means that 1/3 is a 0 of the function. All right, that's one of them right there, 1/3. Now, let's go back and let's talk for a second. This was a degree 3. That was a degree 3. We just divided out by a linear factor. So we're left then with a quadratic. And once you get down to this quadratic, then write that quadratic over here, 3x squared plus 9x minus 6. Set that equal to 0 and factor that if possible. If we pull a 3 out, that's x squared plus 3x minus 2 equals 0. Can we get that to factor? Two numbers that multiply to be -2 add up to be 3? I don't think so, because we'll have to have a -2 and a +1, and that won't add up to be 3, or vice versa, it still won't add up to be 3. So factoring won't work. How about we use quadratic formula here? Sure, quadratic formula, x equals opposite b, so -3 plus or minus square root b squared, 9 minus 4 times a times c, all over 2 times a, which is 2 times 1. Cleaning this up, we'll have negative 3 plus or minus the square root. That's 9 plus 8, so 17, all over 2. And right there, there's the other two zeros. There's the other two zeros. So one of the zeros is right here at 1/3, and the other two zeros are right there at negative 3 plus or minus the square root of 17 all over 2. If you're a little bit iffy on this, that's okay. Hang on. We're going to do a lot of these over this week and next week. So we got this. All right, last one for today. Let's look at this problem. If I can find it, there we go. I want you to find the zeros and factor f of x equals x to the 4th minus x cubed minus 6x squared plus a 4x plus an 8. All right, 5 terms. Can't factor anything with 5 terms. So let's use this new concept of the p over q factoring. P is all the factors of the constant. So that's plus or minus 1, plus minus 2, plus minus 4, plus minus 8. Q, all the factors of the leading coefficient, plus or minus 1. And P over Q is all these P values over Q. Well, it's just the same as P. Plus or minus 1, plus minus 2, plus minus 4, plus or minus 8. All right, now, you can substitute in, as we said before, but personally, I like to do synthetic division, so I always start right off the bat with a synthetic division. So let's start with positive 1, and we're going to have a 1x to the 4th, a negative 1x cubed, minus 6x squared, plus a 4x, plus an 8. And running through synthetic division, bring that 1 down. That's 1 multiply, 1 add, 0. 0 times 1 is 0. Add these guys, that's negative 6. Negative 6 times 1 is negative 6. Add, that's negative 2. Negative 2 times a 1, negative 2, add 6. There's your remainder. Not 0, so we know that 1 is not a 0. Let's find negative 1. Bring the 1 down, multiply. That's negative 1, add, negative 2. Negative 2 times a negative 1 is 2. Add these guys, that's negative 4. Multiply, that's 4. Add 8. 8 times negative 1, negative 8. Wahoo! That means we had a remainder of 0, which means negative 1 is a 0. Negative 1 is a 0, which means that x plus 1 is a factor. That would have been the factor that produces that negative 1, 0. Okay, now, a couple other things. This part right in here, these coefficients that are left after you have divided out one of the zeros, these coefficients are called the depressed polynomial. It's not sad, it's just smaller. We've divided out something. So once we get a 0, then we work with the depressed polynomial. And we keep going from that depressed polynomial. So now I'm going to start again with the depressed polynomial, negative 2, negative 4, and at 8. Okay, listen carefully. I do not want to check 1 again. It didn't work the first time, it won't work again. I do, however, want to check -1 again because it might work twice, which would mean we would have a multiplicity of 2 on that -1. So things that work, you do want to check again. Things that don't work, you don't have to worry. They're never going to work. They didn't work the first time, they won't work the second time. So we'll try here. So we'll bring the 1 down. -1, add, that's -3, 3, -1, 1, 9. All right, so that means that -1 did not work again. Did not work the second time, so now the -1's done. So let's work with this depressed polynomial. We have 1, -2, -4, and an 8. Let's check one of these next numbers down this list. So we're done with the 1 and the -1. Let's try a 2. Bring the 1 down, multiply, that's 2. Add, that's 0. Multiply, 0. Add, -4, multiply, -8, 0. All right, another remainder of 0. That means that right here, this 2 is a 0. 2 is a 0, which means also that x minus 2 is a factor. All right. Now, let's think. We started with a degree 4. Took out a linear term right here, that x plus 1. We got down to a degree 3. Did a division on a degree 3. Took out this linear term of an x minus 2. That leaves us with, this is a degree 2. Once you get down to a degree 2 or a quadratic, then flip back into x's, and this gives us x squared plus 0x minus 4. Set that equal to 0 and solve like normal. This will factor into an x plus 2 times an x minus 2. We have a -2 and a 2 as the 2 remaining zeros. So if we line everything out here, our final solution, look back, directions, find the zeros and factor. The zeros are -1, 2. Oh, but look at that 2. It showed up here and it showed up there. So 2 with a multiplicity of 2, and we also have a -2. Factor, if we want to factor f of x, that's going to be x plus 1 times x minus 2 squared, because that was a multiplicity 2, and in this last one, an x plus 2. Okay, there we go. Again, if it's a little tricky, you're not used to doing things like this, if you're still a little confused, that's all right. We're going to spend several more days on this, not to worry, and maybe watch the video again and see if that helps and kind of listen again. Okay, good luck. Have a nice weekend.